we ended yesterday, or Monday. We ended last time by me asking you to work out this formula and make sure that you can get the chi-square statistic. Remember, the formula is basically a way of scaling and figuring out how far away our observed values are in the sample from what we would expect the distribution to look like. How far away are the observed from the expected? And our p-value is going to be stating the probability that the observed is that far away from the expected. So here are the components of the formula. There are 6 components, 1 for each color. There they are.
That's so fancy.
It's like the fanciest thing I have in any PowerPoint all year. So these are each of those. These are each of those components, and then here they are. So the blue one is this one. The orange is here. Here's the green. Here's the yellow, and so on. And we should get 10.180. So I will read this out because I basically said it already. Think of chi-square as a measure of the distance of the observed counts from the expected counts. So large values of chi-square are stronger evidence against the null hypothesis because they say that the observed counts are far from what we would expect if the null hypothesis were true. Small values of chi-square suggest that the data are consistent with the null hypothesis. So smaller values of chi-squared are going to give us larger p-values and make it more likely that we're going to fail to reject our null hypothesis. Remember, our null hypothesis here is that the distribution of colors is what they say it is. And then the alternative is that one of those proportions or one of those values is different. You're leaving off squares. This should have a squared. This should have a squared. Some other things should probably have a squared. So it was a calculator thing, not a formula thing. All right. So, continuing. So chi-squared, just like t, is a different distribution from the normal distribution. But t looked pretty close to a normal distribution. Chi-square distribution does not. Here is what our distribution looks like here, and it is a skewed right distribution, pretty heavily skewed right distribution. And like how skewed it is and where the peak is depends on how many degrees of freedom we have. Remember, degrees of freedom is going to be, for these, is going to be the number of categories minus 1. So how many different color M&Ms were there? There were 6, and so the degrees of freedom is 6 minus 1, which is 5. And so if we want the chi-squared statistic and the p-value from the chi-squared statistic, we're going to pull out the calculator. There is also a table for chi-square on your formula sheet, but we're going to use the calculator. And we're going to go into the distribution menu, same place that normal CDF and all those are. You're going to be able to do this in stat tests eventually, but I'm going to show this here. We're going to go chi-square CDF. And again, it's going to have lower, upper, and then it's going to ask for degrees of freedom. So our lower is the 10 point, what was it, 10.18? And then our upper is going to be a really big number. So everything to the right of 10.18. Degrees of freedom was 6 minus 1 was 5. Huh? The 6 is number of categories minus 1. So for the M&Ms, there were 6 different categories, the categories being the colors. So that minus 1 being 5. And so that would be around where the p-value would be. It's the chi-square statistic that we got on the last problem. Chi-square CDF.
So the calculator's not even that helpful. We have to do the whole thing by hand anyway. No, he's saying we'll eventually be able to do it.
Eventually we'll be able to do it.
Wait, so lower is the 10.18?
Lower, upper. Yep, lower is 10.18, and then the upper is a really big number. 0.07 something. So we are finding, that is this kind of right tail area is what we are finding, and that will give us our p-value. So again, how the distribution looks, it's generally going to be a right skewed thing, and how it looks is going to depend on degrees of freedom. There is a table that you can use in your formula sheet if you would prefer to do it that way. So here's my chi-square with degrees of freedom of 5. The p-value is the proportion that's to the right of that chi-square statistic that we got. And so the distribution would look something like this. Here's degrees of freedom of 5. And we see in the table that the p-value would be between 0.1 and 0.05. Most of you are going to use the calculator. But if you do want to use the table, that's where it would be. So the p-value is between 0.05 and 0.1. We saw that it was 0.07. So at a 0.05 alpha level, we're going to end up failing to reject. So here's our fail to reject sentence.
Why is it now, instead of just the alpha level, it's between 0.05 and 0.1?
On your, if you're doing it on the calculator, you're going to write the specific p-value. Right, the p-value of 0.07 is greater than alpha of 0.05.
Gotcha.
It is just because they're using the table, and the table doesn't give specific values. We're seeing, in degrees of freedom of 5, it sits at, my 10.18 sits in between the 9.24 and the 11.07. So that means that the p-value must be between these two. That's what the table would tell us, which is bigger than 0.05. So we are still saying that it's greater than our alpha level of 0.05, and you would give the p-value the same way you have before. So there's not enough evidence to say that the distribution there is incorrect.
Is it Mrs. Corkin that does this all the time?
Gotta love Miss Corkin. All right. Here come your conditions. And we have a substitution because this distribution, since it's so right skewed and is dependent on our degrees of freedom so much, this distribution is not a normal condition. So the normal condition is getting replaced. We still have random and independent, but the normal condition is getting replaced. Use the chi-square goodness of fit test. Actually, I'm going to just go through and let's see. Actually, let's back up and go here. Random sample or randomized experiment. Independent. Either the observations are independent or a 10% condition. And then this is my other condition, which is the large sample size condition, that we're using a large enough sample size. And the way that we're doing that is pretty similar to what we do when we do proportions. Remember our like n times p and n times 1 minus p? We're going to do something pretty similar to that, where we are going to calculate out all the expected counts, which you need to do anyway for the formula, right? Observed minus expected squared over expected. You need to calculate out those expected counts anyways. And so we're going to write out those expected counts and make sure that they are all at least 5. 5 is going to be my benchmark for expected counts. So go ahead. The main thing to write down here is, the main thing you want to write down here is to say that the normal condition is getting swapped out for this, all the expected counts are at least 5. For any chi-squared test, you're going to check that all the expected counts are at least 5, yes. So that's what we're going to do. These are going to be the conditions for all of the chi-squared tests, all the hypothesis tests that we're doing this chapter. And the formula is going to be that sum of observed minus expected squared over expected. So this is the one to make sure you write down, and you should say that it's taking the place of normal condition. Expected counts being at least 5. All right, now for the part that's in your notes. Here's the outline of the 4-step process. Step 1, we're going to state out our null and alternative. Our null and alternative is that the distribution is what it says it's supposed to be. The alternative is that the distribution is not correct, or that at least one of the proportions that we're reporting is not what it says it is. At least one proportion is not right. Then step 2, we're going to check our conditions. Remember, the normal got substituted out for all the expected counts are at least 5. And then random and independent. This is called a chi-square goodness of fit test. Goodness of fit. Chi-square goodness of fit test. So we are seeing how well the proportions that we report are fitting our data. So chi-square goodness of fit test, because there are 3 different chi-square tests. So this one specifically is for chi-square goodness of fit test. And the way you're going to tell it apart from the other chi-square tests we're going to do is that this one is about 1 variable. The others are going to be keeping track and comparing 2 different variables. This one is just keeping track of 1 variable. In the case of the last example, it was the color of the M&Ms. That was our variable. So chi-square goodness of fit is going to be about 1 variable. The others are going to be about 2 variables when we get to section 2. Two things to make sure, this is like common errors to make sure that you stay away from. So if you want to kind of snap a picture of this. First thing, you should use observed counts and expected counts. Don't try and deal with proportions here. The only place you should deal with proportions is in a null and alternative hypothesis. In your calculation for observed minus expected, those should be counts. Those should be numbers. Those should not be proportions. And same thing, when we're checking the large sample size conditions, you're going to use the expected counts being at least 5, not the observed counts. That condition is all the expected counts being at least 5. So those are kind of your 2 big things to be careful of here. shift my calculator over here. All right. So now let's do an example. Show out this 4-step process. Are births evenly distributed across the days of the week? This table shows the distribution of births across the days of the week in a random sample of 140 births from local records in a large city. Do these data give significant evidence that local births are not equally likely on all days of the week? So the first thing I want you to do is go into your calculator and put this data, these 7 entries, into list 1. So you're going to go stat edit. That's going to bring you into your list 1. Follow along. So you're going to put your data into list 1. And while you're doing that, think about what the null and alternative hypothesis are going to be here. 23, 24, 20, 27, 18, 15.
How would you start the sentence for step 1 for this? Like, how does the start of the sentence go?
The first thing you should write in step 1 is null hypothesis.
So it's different than how we did the other ones. Because for the other ones, it always started with a sentence.
You can start with a sentence.
Oh, that's
Like,
fine.
we are performing a hypothesis test of.
Gotcha.
Like sometimes I'll write out that sentence. But the thing that you absolutely need to write is null and alternative. Define any variables you're using in your null and alternative, and say what your alpha level is. We're going to use 0.05. So you should have data sitting here in list 1. So this is what your calculator should look like right now. Null hypothesis. It's basically stated out in the first sentence what the null hypothesis is.
That they're evenly distributed.
That what are evenly distributed?
The
Births are evenly distributed across the days of the week. So the alternative is that the births are not evenly distributed across the days of the week. In terms of proportions, that means that the probability that you're born on any given day of the week is what? 1 in 7. 7 days in the week. So you're equally likely to be born on any particular day of the week. And then the alternative would be written as at least one of those proportions is not 1/7. So we can write that in 2 different ways here.
We don't have to have like we want to perform a test stuff, right? I've never done that.
Say again?
Do we have to have that we want to perform a test
No.
stuff? No.
You want to make sure that you're stating null alternative. If you're writing it this way, you should say what each of these proportions are. Maybe you're using like p sub 1, p sub 2 up to p sub 7, and you want to say that p sub 1 up through p sub 7 are the proportion of people that are born on Monday, Tuesday, Wednesday up to Sunday. Or if you're stating it in words this way, you don't need to define anything. You should also put your alpha level 0.05.
So then where are you defining what each of them means? So you said like we're not doing 2 different tests. It's not 2 different samples. It's not something.
Proportions of births on all the days is where they're defining what these stand for.
Oh, right. Okay.
You good? Okay. Again, this is called a chi-square goodness of fit test, so that's the first thing that should go in step 2. Step 2 should say, we're performing a chi-square goodness of fit test. And then you should check your 3 conditions. Random. What do we say for random?
Random sample of 140.
There was a random sample of 140 births. Independent.
People's birthdays are independent of each other. Your
Yeah.
birthdays
Or
don't affect someone.
140 people, 10 times that, 1,400. More than that amount of people that are newborn in a large city. Then our new condition is expected counts. So how we're going to get our expected counts is that, what's our total sample size here? 140. And we would expect 1/7 of them to be in each one. All right. 1 second.